it's my pleasure to introduce Professor Ellen Kuhl, who is the Walter B. Reinhold Professor in the School of Engineering, as well as the Robert Bosch Chair of Mechanical Engineering here at Stanford. So she's passionate about improving human health through computational simulation. Her expertise is in living matter physics, which is the use of theoretical and computational models to simulate and predict the behavior of living matter. So we're going to learn a lot more about that in a second. And one thing that was interesting in your bio, kind of a subset of that, is you're also a founding member of the Living Heart Project, which is a translational project that's aiming to revolutionize cardiovascular science through the use of realistic simulations of the human heart, presumably. Yes. And so in addition to that, I should also add that she is also quite an athlete. So you are a three-time qualifier for the Kona Ironman World Championship, as well as a three-time All-American triathlete and a marathon runner, including the Boston and New York Marathon. So what you do as an athlete in your spare time, most of us would do as our full-time job. But we're super excited to have you here today to learn a little bit more about this idea of automated model discovery and how that's revolutionizing science right now. So I think a great place to start would be if you could just give us a little bit more about your background, and in particular, the Living Matter Lab and what you're researching and doing.
Yeah, sure. Yeah, thanks for having me. So so in the Living Matter Lab, what we do is we design physics-based tools that we embed in machine learning, and then we model living systems, as you just said. And you mentioned the heart, so we're doing this for the heart. We do this also for arteries, for the lung, for muscle. And then most recently, what people find most interesting is the brain. And we work a lot here at Stanford with people in the clinic, people who design or use devices, for instance, heart valves that go into the heart, kind of to help them design a therapy that's targeted for a certain person. And then because I'm an engineer, it's always centers around forces and stresses to really understand the forces in the heart that these devices change.
And so could you give us a little bit more about, I mean, obviously a part of that is modeling how the heart works. So how, we're going to get into the automated model discovery in a second, but how what's one special about soft matter versus, say, modeling something like a steel or a metal? And how was that done in the past?
Yeah, that's a great point. So the way people have done this in the past, I mean, people have modeled materials like for a century probably, and they've always gone and tested it, and then they fit some data points to a curve, and that was their model. And so a lot of people have attached their name to a certain model. So you probably know the Hoek spring. There's for rubber, there's the Ogden rubber model or the Mooney rhythm model. And so people have just attached a name, and now years later, you can just go to a library of models and say, I want to use the Holzapfel model, which is developed by Gerhard Holzapfel. And so now you just go through this library of 100 different models, and then you fit your material to that one model that you like. And that's important because then you can test, you can use the model, and hopefully also predict what it would do in other settings, right?
And how are those, so how do you go about selecting that model? Does that require that you have an expertise? And I mean, what level of expertise, or how does that happen? Do you need to be
so I think you're hitting the critical part here, and that's really finding a good model. And so in the past, people were just selecting one of this big library of models, and they would just go in and find the one that they think is good. And to do that right, you would probably have to read a lot of books on material modeling, or take classes in continuum mechanics, finite elements as a student, or read up on it in manuals of textbooks. It was really limited to experts in the field. And I think what we found really tricky when I teach students is to teach them to use the right model and select the best model, because it really requires experience, and it limits the use of these tools to really people who are super well trained in it, right? And so what we thought is, can we automate that process and make that more available to broader usership of people? When I work with someone in the hospital, they're not experts in mechanics or physics, they haven't taken these classes, and still they want to model something. So can we make it safe for them to use these tools?
And so that leads us maybe to automated model discovery, which is kind of the focus here. So can you talk about a little bit about what this process is and how it's different from that old process of someone created a model and then you go into a library of potential models and you select one and then apply it to your situation?
Yeah, and that's the great question, is can we automate that process? Can we take the user out of this equation of selecting and actually make it less prone to error, right? And so what we have done, and actually it's a very new method that people have started to developed over the last 2, 3, 4 years is they use neural networks to help select the model. And so then you kind of feed the information that you have into the network and use networks that were traditionally developed for just other things. I mean, they're very powerful tools for image recognition, for example, but now tweak that and use it for model discovery.
Okay, and then, so can we back up? So you said model discovery. So it's model discovery, and is it at the same time sort of selecting? So can you walk through it one more time, like how that would work? So I'm a hospital, say I'm a doctor or something who does not have a background. How would I apply this, or how would I use this? I would have a set of data, or I would have a situation I want to apply it to, and can you walk me through that a little?
So ideally you would have data, but data meaning, for example, if we model, say, the heart, there would be tests, and ideally they're different tests. So you can do like tension, compression, shear, twist tests on little samples of heart tissue, and then you just feed that information into the neural network. If you don't have that now, I'm assuming you don't have that at hand, we have a website where we have collected databases for heart, for cardiovascular tissue, brain tissue, rubber, just so that you can get started and play with it. And then that gets fed into the network as pretty much the input to the network. The network just runs, and then it gives you a model and it gives you model parameters at the
end. So you talked earlier about sort of designing something for a particular heart. I mean, does this work in terms of, is there a difference between modeling hearts in general and using this to model a particular heart? Is there ability to sort of personalize the model that you're using to fit the person that you're developing something for?
So depends on what kind of tissue you want. In this case, you probably don't want to give me a piece of your heart to test. But in general, so some pieces of tissue you can just harvest from a person and test, and people do that. Or you would have an age group selection down the road where you say, okay, this is a 50-year-old male, has this kind of healthy heart conditions, and we have a library for that. And we're just starting to build these things, but that's a great question. The question is, how much does it differ? And I would say probably in a healthy person, it differs by some magnitude, but not too much. So you could probably live with someone else's data that others have collected.
So if you already have the data library, what would be creating the different, what are you adjusting to create a different model?
So right now we're at the process of developing this method for general things.
Okay.
So when we have a data library on the heart, we could run it through and develop it, discover the best model. Why is this different from what people have done? So what people have done is they have just used the model, they have fitted, but there's probably hundreds of models and you don't know it's the best.
Okay.
Also, what we do is we combine different models. So the network, you can think of a neural network having a number of different nodes, say about 20. So the model can discover 2 to the power of 20. So that's 100,000 or more, 1 million different models.
Okay.
Because it can combine different and mix and match different terms. And so we have done this and tried this. And actually, sometimes we discover models that already others have used, which is nice, because out of this 50,000 models, you discover the whole subfield model, which is great. But sometimes you don't. And then you ask yourself, okay, would people have found this with any other way? Probably not, right? Because you wouldn't screen 50,000 different models by hand. And so this is actually great because you have this vast overview and library of things you can choose from.
That's interesting. And so neural networks have been around, well, for a fairly long time, but there's something unique about the way you're doing this. And I'm going to read it here because it's called constitutive neural networks. So what are constitutive neural networks and how are they, what was the challenge with the traditional neural network and how did the constitutive neural networks address those challenges?
That's a great point because you could technically go ahead and just use a neural network to do this, right? You would take a neural network off the shelf, feed in your data. Neural networks are great at fitting functions. Actually, with any number of these nodes, they could approximate any function to any degree of accuracy. That's just a proof to show this. But we want to fit a specific function, and we don't want to use it for something like image recognition, where it is very good off the shelf, but we want to build physics into the network. And we know the physics. So for example, we know when we pull on something that usually, and this is say an artery, it gets harder over time to pull. So it's kind of like having this exponential stiffening behavior. And we want to kind of build that information in. And we also want to build in that in physics, if you measure forces over deformation or stress over strain, you kind of have a curve and not a zigzag. And all that is, in a way, built in the network. So we hardwire physics into the design, into the input, into the output, into the architecture of the network itself, and into the activation functions. And after we've done this, you, as a user, don't need to worry about it. So this network that we have automatically now satisfies all the physics. And this is a trend that has been around for the last 5 or maybe 10 years for constitutive models, probably only 3.
Okay.
And it's constraining this huge space of functions that a neural network would search over.
Just putting sort of rails around or guidelines around it, so you're not getting something that violates the laws of physics.
And then you come with something that actually you know already a priori that it satisfies everything.
And are those what you're? And this is, sorry, I'm a not technical, so my question would be, the guidelines or constraints that you're putting in around it, the physics, are those models themselves, or are they? Does that make sense? Are you kind of having the model develop in relationship to existing, to how we model certain things like stretching of arteries?
Yeah. So for example, we can say there's a certain symmetry to the material. So it's the same from every direction that you look at it. We can build that in, or you can build into it that when you load it and load it, it behaves the same way. So it's elastic. And certain things you can just hardwire in. And then also we want to make sure that all these existing models that people have developed are a sub part of this. So this is a natural generalization of what people have done, but much, much broader. You can think of a couple of thousand models in this one network.
And we had a question, so I do want to get to this. We had a question earlier come in about using these models. I mean, is this something that's only being run at Stanford with, like high performance computing or supercomputers, or is this something that someone can do at home or at a hospital or with more modest resources?
Yeah. I mean, we run this on a laptop just like this. We have all the software on a GitHub repository from our lab, so you can find this on our website. You can just link it. And also what's super cool and what I'm most excited about is if you want to use this, a lot of people use this for what's called finite element simulation. So they want to model real structures, like the real heart. And so we've teamed up with Dassault Systèmes, which is a company that actually has one of the largest finite element packages called Abacus. And what they do is they use our output of the network to really use it, immediately feed that into their simulation. So there's like a direct handshake between what the model produces and what the finite element simulation can take in as input. And this is very general. So while this is one example, you can just already download it from our website, but you can also translate that into any other package. So the idea is it's not just a standalone, but it feeds immediately into a simulation that anybody wants to do with like a larger structure.
And I have a thought, we have a good question about kind of the applications of this, but before we maybe jump into that, one other thing that I read about these is that so one of the concerns about a lot of algorithms or neural networks is they're black boxes. It's very hard, right? You get an output, you don't know how it's getting there. My understanding is the constitutive neural networks, as opposed to that, are a little bit more interpretable. It's you're able to understand the model. Can you mentioned that already, but could you maybe elaborate on that?
Yeah, thanks for actually bringing this up, because that's true. So a lot of times when you just run a neural network, you get some bit of a curve, but nothing more than that. And so here you really get some information about, say, the stiffness. So it gives you parameters that have a unit of a stiffness, or a shear modulus, or a Poisson ratio, or just common physics parameters, and also interpretable terms. So you have a term that's linear, where you see in the curve it's linear, and then overlaid a quadratic function. And one can be related, say, to the matrix material of the tissue, and one can be related to collagen fibers. So you can really interpret the terms, and the parameters that are otherwise just network black box parameters really have a physical meaning. So they're real physics parameters.
And so does that give, I mean, especially if you're using this for developing a medical device, does that give you more confidence in the accuracy of the models, or what does it, can you build on what it means for it to be more interpretable?
Yeah, it's a lot more helpful. So because there's this vast body of literature where people have done studies in the past, so you can compare, for instance, we now put some data into the network, you can say, oh, this compares well to a healthy artery, or this looks more like a diseased artery or something, right? So you kind of have a great base of comparison. People, and exactly, I think this is a criticism from a lot of people in physics, or in our case, engineering, that neural networks don't use any of our prior knowledge. And for decades, engineers or physicists, mathematicians have really built tools and an understanding and insight into things, and you don't want to just lose that.
Right. And I'm just a quick, because we see we got a great question about, so the models, are they open source? There's a link in the interface to the Living Matter Lab, and I believe there's a link to the GitHub repository.
Yeah.
So you can find a lot
of. So
of.
if anybody can't find that, just reach out and we're happy to point you. But it's all on our GitHub, and it's called GitHub Living Matter Lab, and so you'll find it there.
So if you're interested in learning more about it or sort of playing with it. Well, and to that point, what are some of the applications, or what are the things that you're most excited about in terms of this process, the automated model?
So I can give you an example of something that people have previously not studied, where this is cool. So over the summer, we've, with a bunch of undergraduates in our lab, we have tested a lot of artificial meat. And so there's a cool application because a lot of people claim that the perception of taste is related to the stiffness of the meat. And so you think about, you eat like super soft tofu and you feel it doesn't taste right, and it's not a good meat replacement, right?
Interesting.
And so the idea is of these products to match the mechanical signature of real meat. And that's not just the stiffness, but also the fibrous aspect. So it's usually anisotropic. It has a certain fibrous structure that tissue has from, this is muscle tissue mainly. And so they try to recreate meat that has the mechanics of real meat. And nobody has a mechanical model for artificial meat. So we're like, oh, we can discover this with our network. And actually it works quite well. So we just have tested a bunch of, like, the entire supermarket shelf. and actually it was really cool study because the students learned how to use the device, to use this new method. And we discovered some models actually out of it. So that was cool.
So that's the future of dining. We'll have a texture, an actual mechanical texture rating.
Well, the real future would be like if we can learn so much that we can design like the best matching material, right?
So what this is doing is you were testing the meat, and from that you were creating a model of how that meat behaved, and that gave you parameters that helped you sort of interpret it.
Ideally, you would now, what you're saying, ideally you would now go back and say, okay, what do we have to change to adjust certain properties of it? Like, when does it fail? How stiff is it? How does it shear? Right.
And what would, this is a little off topic, but what would that look like? Would you then go back and say, well, I presumably now have a model of real beef, of real, and maybe even at different stages of cooking? I don't know if.
Yeah. So, I mean, ideally, if you can put these parameters, I mean, we haven't done all of this yet, obviously. That would be great to have. But that would be a cool thing to do, and then really have all these different parameters that influence the mechanics of it. And then the perception of taste with that. Yeah.
That's really interesting. We have some of these more questions about, so it's obviously one thing if you're testing a sort of artificial meat, where are you seeing the applications in something like healthcare? And I'm assuming and what still needs to be done, because presumably there's a long way from going from modeling the heart to creating or maybe not, to creating an actual.
So we've done this, for example, for the brain. So brain is super soft. It's very difficult to test. It was one of the last materials that people really got their hands on testing. So you mentioned steel. So there's this long history where people initially started testing very stiff materials because it was simple. They don't deform much. They're pretty linear. You could just pretty much stably test them. And then the next thing was muscle, then arteries, and then probably or other softer tissues, gels. And then the brain is the softest of all biological tissues. So it's the last kind of thing that people try to study. If you think of the football players when they get a hit to the head, what you want to do is you want to translate the deformation or the acceleration of the helmet into forces, and those forces you apply to the head. And then you can get a very high resolution response in terms of a stress profile. And then you can even say, oh, this region of the brain is most affected by this hit. Right?
Okay.
And that region is responsible for motor skills or language or vision or whatever. And so you can correlate a hit to the head with a stress profile with a function.
It's interesting. And then in turn, that might translate into how you build a better helmet.
Or safer devices, or even diagnose things, or in surgery, if you have to cut the brain, which region do you want to cut in? What's the safest region? So there's a lot of mechanics actually when you hit the head, and where you can really apply these methods.
So we're getting a question about how about non-living matter, so non-soft materials. Can this be applied to other kinds of materials, and would there be advantages over the traditional methods, or is steel just understood well enough that maybe this is
so yeah, so I think many of the materials in their operating range, like steel, are probably relatively well understood. Materials that are linear are not difficult to discover. You measure 2 points and you fit a line.
Okay.
So it's kind of, from a scientific point, not that interesting probably. But all kinds of gels, rubber materials, like soft materials in general, meta materials where people design materials for certain functions. So all kinds of materials, you can apply it in general for everything. But these are materials where it's probably most impactful. Should also say right now, this is a new technology. We're very confident using it for elastic materials. So when you load them and unload them on the same behavior, they don't have any permanent deformations or damage. Next step would be to take this into something that's time dependent, temperature dependent, damages fails, right? And you could take this method way beyond what it's currently doing. So there's a huge potential to actually explore.
And would that be in collecting more data? So say you're testing a material right now at room temperature, would it be gathering more data at different temperatures? Yeah. Is there a point where that could be worked into the constitutive part of the constitutive neural network where the actual physics of how these behave?
Yeah, for instance, temperature is a good one. Certain materials, polymers, become glassy when it's at different temperatures or change entirely their state. Certain materials fail. So for saying biomaterials, it's pretty interesting to know when they fail, what much of a hit can the brain tolerate. Right? It's not just in sports, but in car accidents, in the battlefield. Right. There's a lot of this that you can actually test and then try to understand better. Or how do these tissues interact with devices? How, if you put a very stiff device, a pacing electrode into the heart, or stimulation into the brain, they're usually out of, not like the engineered materials, metals, very stiff. How does that interact with the soft material?
And how does this work for things like, so we're getting a question about like modeling blood flow or something like that for different, is that a totally different, is that kind of on a physics level a totally different thing to model, or is that something that could also eventually be tackled by this approach?
Yeah, so that's a fluid. So we did have done this so far for solids mainly, but I think you could potentially also do this for fluids. We have actually one application that's just very recent where we looked at how Alzheimer's spreads through the brain. So that's not mechanics at all.
Interesting.
And there we tried to discover a model of the spreading of Alzheimer's disease through the brain based on physics of spreading and growth of this disease.
And so this was a similar thing where you fed it data and then it developed a model, and then you could, so in that case, it's maybe, essentially, so it's then revolutionizing how you understand Alzheimer's or the spread of Alzheimer's. And would that, so does that potentially lead to treatments? How would you in turn, once you have a sense of how it spreads, how does that in turn get applied?
So it helps you understand the timeline. It helps you understand the different regions in the brain that are affected. Ideally, of course, people want to understand if they can halt it or revert it or stop it.
Right.
The model itself would probably not be able to tell you that, but it can give you a lot more information about which regions are affected at which point of the disease, and how does that kind of affect the behavior of the person, the decline in behavior. And that's very different because you work with data that has been collected in patients and people in disease, and not data that you create yourself. So there, in a way, you have a lot of data, but the data are not, you can't manipulate the data in a way, right? You get what you get.
Yeah. We have, so going a little bit off topic, or not off topic, but taking a little bit of a pivot here. So there's this question, we have an interesting question that came up, and kind of if you're testing a single material like the brain, but you talked about modeling like a hit to the head. So of course, at that point, the force is going through skin, the skull. So how do you, I assume there are traditional approaches to that. Does this feed into it, or you have, there's a model of the individual materials and then an overall model of how they interact? Can you talk a little bit more about that, and whether this could be used to model complicated systems with different material?
Yeah, absolutely. So you can do this with finite elements. So you would just take a scan of your head, and then you section it, and we've done that. You section in different regions. So there would be the skull, there would be fluid, there would be the brain itself, there are ventricles that are fluid filled. And so all of that can have different properties. You chop it in little pieces, and every piece you assign a certain material. So you would test the skin and the skull and the brain itself. And then everything has a different stiffness. And then when you hit it, you can automatically see like reflection waves at the interfaces of certain materials. Usually there's stress concentrations of two different materials. So that's very interesting because that's where some diseases happen usually.
Interesting. And then is the model that's coming out one that is I don't know what the word would be, a composite model of all those different things, or you have a models of each of those?
Yeah, it's more each of those. So you have certain regions that have a different material property in a way, if you want.
Well, we could go on, as I'll say, but we're running short, so only 30 minutes. I did want to talk a little bit about the class. It's a class you've run before in the summer, but you're offering it this winter, and it is open to professional students if they're interested in taking it online. So you can find more about that in the interface. There should be a link to the class right there on the upper right-hand side next to Professor Kuhl's biography. So if you want to click on that to learn more about it, but I would love to hear, so what is this class? I mean, what do you need to know? So it sounds like you don't need to be a physicist to take the class, but what is the class? What do you cover in the class?
So in the class, we pretty much cover what we just talked about. We go more in depth. And so we teach how these methods work. We give students access to all the code, which is online, but we explain it. We let them run it. We have a project where they can use it for certain things. It's targeted, obviously, at students who are interested in neural networks and bringing physics and engineering into the network, but it's also targeted, if you want, at researchers, postdocs, who want to use this to study their materials and understand that better or discover new materials. Also probably people from industry who want to design finite element tools and use this to have a very specific material model. Someone who probably doesn't have that skill set and comes in and doesn't want to take years and years of classes. So I envision that down the road, this class will probably replace all these classes like continuum mechanics, finite element modeling, solid mechanics, because this is all automated at some point, and the theory is built into the network. Right?
Interesting. Or maybe not replace it, but fewer people maybe will take those. It'll be another path through. Yeah. And so, but it sounds like there's a broad application, and there are both people who want to, who are maybe have taken those classes and have the training in the background and want to develop new models, and also people who want to use the models who don't have that background and want to apply it. So that's really interesting. Well, we're just about at time, and so I appreciate all of you joining us today and for your questions. I know we only got to a handful, but you have the opportunity either to go to Professor Kuhl's lab. Again, there should be a link there should be 3 resource links. It's right at the top, the Living Matter Lab. All the code is available there through GitHub, as well as some of the papers talking about the applications in more detail. And then and if you're still interested, you're welcome to join the course if you want to get a deep dive. And so that will be offered through Stanford Online. It is you can click on the link to learn more about it. It'll be offered this winter quarter. I should warn, it is a graduate level course, right? So it will require, it is an intensive course that's probably 10 to 15 hours of work or something a week. So it's 9 hours. That's right. It's not 3 units, so 9 hours. Well, no, but it's a rigorous course, right? So it's not, it is something where you'll really have a chance to kind of dive into the models and understand it and look at the code. So thank you again, everyone, for joining us. And as see the last question coming in, yes, the recording of this presentation will be sent out. So if you missed something or you want to watch it again or share it with a colleague who might be interested in this, we will be sending that out in about a week to everyone who registered for the session. And again, you can also send any colleagues to the Living Matter Lab to learn more about this really interesting topic. So thank you, Professor Kuhl, and thank you, everyone, for joining us today.